In this lesson, we're going to look at applications of exponential functions. In this problem, we have the population of Smallsville growing exponentially. The population was 5,000 in 1960 and grew to 9,500 in 1962. Part A would like us to write a formula for the population of Smallsville in the year t since 1960, in which case t equal to 0 would be 1960, and we know in 1960 the population was 5,000. So we'd have the point 0, 5,000 on our function, and 2 years later in 1962 the population is 9,500, so we would have the point 2, 9,500, and we can use these 2 points to find our exponential function a b to the t, where a is our initial value, so we already know a is 5,000, and b is our growth factor, which is 1 plus our percent rate of change. In order to find that, we should look at the ratio of our two formulas. E of 2, which is ab squared, over e of 0, which is ab to the 0, which we can cancel the a's. B to the 0 is 1, so we get b squared. Also, if we look at the ratio in terms of evaluating, we get 9,500 over 5,000, or plugging that into our calculator, that's 1.9. So then b is the square root of 1.9, or approximately 1.38. So for part A, our formula, E of t, is our initial value 5,000 times our growth factor 1.38 to the t. For part B, we would like to know how many years after 1960 the population will double. So we need to set our formula equal to twice the initial amount, or 10,000, and then solve for t. So we would like to isolate the t, so the first thing we're going to do is divide both sides by 5,000, in which case, rewriting it down here, running out of room, we get 1.38 to the t equal to 2. And then we can take the log of both sides. I like to use natural log, so natural log of 1.38 to the t is equal to the natural log of 2, in which case I can bring the exponent down to write t times the natural log of 1.38 equal to the natural log of 2, divide by natural log of 1.38, and we get that t is approximately 2.15 in years, in which case we know that it takes approximately 2.15 years for the population to double, which makes sense when you look back and see that in 2 years it almost doubled when it was at 9,500. Let's look at another example. Here we have a population in 1980 of a town being 10,000 people. It grew by 3% that year. Part A wants us to find the formula for the population of the town t years after 1980, assuming linear growth. Okay, if it's linear growth, that means we have the equation of a line, mx plus b. Our initial value is our b, which we see is 10,000, and we have to figure out our slope. Since the population grew by 3% in 1 year, we can figure out the slope by multiplying 10,000 by 3%, which numerically is 0.03, or 300. So our linear function is going to be 300x plus 10,000. For part B, we want to find the formula of the population of the town t years after 1980, assuming exponential growth. So we'll have an exponential function, a times b to the x, where a is our initial amount, b is our growth factor, which is 1 plus our interest rate, which in this case is 3%, or 0.03, in which case we can plug that in to get our exponential function equal to 10,000 times 1.03 to the x. and we have our two formulas. For part C, we want to know which formula is a better fit if the population of the town in 1990 was 14,000. So we should probably evaluate these two functions in 1990, which is 10 years later. So the linear function evaluated at 10 is 300 times 10 plus 10,000, or 13,000. Our exponential function evaluated at 10 is 10,000 times 1.03 to the 10, and plugging that into our calculator, we get approximately 13,439. This one is closer to 14,000, so the exponential is a better fit. Okay, let's look at one more example. In this example, we have a radioactive substance that decays at a rate of 10% every 5 years, and we want to know what the half-life of the substance is. But it doesn't give us an initial amount. So let's let the initial amount just be A. In which case, we have the point 0A on our graph, or on this function. And then, 5 years later, we have 10% less of A. If we have 10% less, we're left with 90% of A. So we have those 2 points, and we can use those 2 points to find the formula of our exponential function. A times b to the x. So just like in 4, we'll look at ratios. We'll look at e to the 5 all over e to the 0, which is ab to the 5 all over ab to the 0. If you look at it in terms of evaluating the function, the a's cancel and we get b to the 5th. But evaluating that, we get 0.90a all over a, which cancels, so we get b to the 5th equal to 0.9. Now that we have b to the 5th equal to 0.9, we see that b is equal to the 5th root of 9. And I'm going to leave it like that so that I'm not plugging that in my calculator and getting an approximation of the value. And I need to find out when this function, which is a, 0.9 to the 1/5 to the t, is equal to half of a. In which case, the a's actually cancel. And so now I'm just solving 0.9, which I can write the 1/5 to the t as t over 5 equal to 1/2 or 0.5. So I'll take the natural log of both sides. I can bring the t to the 5th down, in which case I'll multiply both sides by 5. I'll get t natural log of 0.9 equal to 5 natural log of 0.5 divided by natural log of 0.9. So t is that amount, which when I plug that into my calculator is approximately 32.9 years. So the half-life of this radioactive substance is about 32.9 years. And that completes this lesson.